Welcome to lesson 2 of game theory. In this lesson, I'm going to talk about something called the normal form of a game. Games can be represented more formally using something known as the normal form. The normal form of a game includes the following information, and this will carry on to the next slide. So first we have n players. The examples we've seen so far, we just had 2, but you can have more than 2. A finite set of pure strategies for each player. We talked about pure and mixed strategies in the previous lesson. The possible pure strategies for player I represented by this set here. You notice the first subscript I is the same because that represents the player. And then the second part of each subscript is the pure strategy. So in this example here, player I has n sub I strategies. And just a note, you don't have to have the same number of strategies for each player. We've been pretty much symmetric with our prisoners game and the pitching pennies, but you can have a case where, maybe player 1 has 3 strategies, but player 2 has only 2 strategies. So that's also possible. And just to emphasize and sort of repeat what we mentioned, that pure strategy in game theory is a complete deterministic plan that tells a player exactly what action to take in every possible situation they might face during a game. A pure strategy leaves no room for randomness on the player's part. They commit to one specific choice with probability 1. So we saw in the rock, scissors, paper game where even though we didn't prove it, I mentioned that the best strategy was to go with probability 1/3. Each player would try playing the different of the 3 strategies. So that would be a mixed strategy. If you just always played one strategy, that would be a pure strategy. And you might do that in some cases. We'll talk about dominant strategies where it always makes sense to play just one. In normal form games, simultaneous move games represented by payoff matrices, a pure strategy for a player is simply one of the rows or one of the columns, i.e. one of the available actions. Always play this row or always play that column. Okay, so there's a few more characteristics of a normal form, and I have that on the next slide. We have a couple more characteristics of normal form on this slide here. Once a set of pure strategies are known for each player, one can define the set of possible strategy combinations known as strategy profiles, which is the set S equals the cross product of each of the possible strategies for player 1, player 2, all the way up to player N. And this is basic set theory. So in general, in set theory, the cross product of n finite sets is a collection of n tuples where the first term can be any element from the first set, or S1 in our case here. The second term could be any element from the second set, or S2, and so on. So I have a concrete example. In the rock, scissors, paper game, we have here one strategy profile, S11, S23, and this is saying player 1 plays rock. Rock is the first strategy, and player 2 plays paper. Okay, so that's a particular strategy for each of the 2 players. Then I have a note here about subscripting, which will probably come up later, and I'll bring it up here, and I'll probably, as I say, I'll probably need to bring it up later on when we talk about some proofs. So while the double subscripting notation is more expressive and accurate, it is difficult to represent general element of S, one of these elements in here, using double subscripting. So for example, if we went with this style here where we use letters, then this pairs player 1 with strategy A, player 2 with strategy B, and so on up to player N with strategy Z, giving the false impression that the game has exactly 26 players. So if we want to do something more general, could use a notation like this: S sub 1, A sub 1, S sub 2, A sub 2, where A sub I is an element from this set from 1 to N sub I, so that S sub I sub A sub I is an unspecified strategy for player I. Okay, so I realize that's a bit to take in, but if you wanted to actually show a general element from this set here, this is the notation you would need. Now, I've sometimes taken an alternative approach where I'll just drop the player's name and I'll just put the strategy in there. So we have here S being an element of little s being an element of this set here, and I've just called it S1, S2 up to Sn, in recognition that there's n players here, and that's less general than this notation here. What you run into is a problem if you need to talk about several strategy profiles in the context of a proof, and since you don't have this second subscript in here, you would need some other type of notation. So for example, you could do this here. So this would be one element from this cross product, and then this would be another element. Okay, so maybe this is a bit to dump on you early, but hopefully when we come to this later on, it'll be a little bit less confusing. So the main thing to remember here is that we're just trying to list all the possible combinations of strategies. So, if you have 2 players and each player has 2 strategies, then you have 4 possible strategy profiles. It just is one example. And then we have one last property here. For each player I, there's a utility function. We've talked about this in the last lesson. U sub I that maps from each possible strategy profile to an associated payoff for player I. So we can look at our example here from rock, scissors, paper. And remember, this was player 1 playing rock, player 3 playing paper. So player 1 would lose because paper wraps rock, and so you would have a -1. And the U sub 1 is just the payoff for player 1. Then U sub 2 is the payoff for player 2, but this is a zero-sum game, and so we know right off that this would be 1, since these two would add to 0. On this slide, I want to talk about strictly dominant and weakly dominant. They're closely related. The idea is fairly simple. A strategy S sub IX for player I is said to strictly dominate a strategy S sub IY for the same player if no matter what the other players do, S sub IX is strictly better than playing S sub IY for player I. So let's look at an example. We have the prisoner game here, and my claim is that strategy B1 strictly dominates strategy S1 for player 1. And we do that by just looking at the payoffs, these U sub I, in this case U sub 1. And we see that 0 is greater than -1, and -2 is greater than -3. So player 1 is always better playing this strategy B1. In a similar way, we can look at player 2, but we need to look at the second term in the tuples here. So we see that 0 is greater than -1 and -2 is greater than -3. So strategy B2 strictly dominates strategy S2 for player 2. So that's the idea. And then we have something called weak dominance, where instead of strictly greater than, you have less than, greater than or equal to. And I have an example of that here. You notice that um, 0, and I'm looking at these two strategies here for player 1, S sub 1 1 and S sub 1 2. You know, 0 is equal to 0, 1 is greater than 0, 4 is greater than 1. So we can't say strictly dominant because of the equality here between 0 and 0, but we can say weakly dominant because it only needs to be greater than or equal to. Okay, so that's two concepts that will come up uh, quite a bit, and that's used to find solutions. So when we saw the solution previously for the prisoners game, uh, player 1 selected their dominant strategy, B1, and player 2 selected their dominant strategy, B2, and that's what left this was the intersection here as a solution -2, -2. A strategy S sub IX for player I is a best response to a particular uh, combination of responses from the other players if and only if the value, the payoff for S sub IX is greater than the payoff for S sub IY. So let's look at an example here that might make this a little bit clearer. For example, player 1's best response to S sub 2 2. So in other words, if player 2 plays this response here, player 1's best response would be S1 3 because 4 is greater than 1 and 0. Okay, so that's pretty simple. If just to do another example, if player 2 played S sub 2 3, then S sub 1 1 would be the best response because 4 is greater than 1 and 1. And if player 2 played S sub 2 1, then in that case, player 1's best response would be S1 3 because 1 is greater than 0 and greater than 0. Okay, so that's yet another concept that'll come up in our discussion as we proceed with our lessons on game theory. So pushing the definition of strictly dominance a little bit further, if you recall, that was just pairwise. We said that one strategy for a player strictly dominates another, but you can have the case where a strategy, and let me point to here, a strategy for a player uh, dominates all other strategies for that player, then that's called a strictly dominant strategy. And then you could also have where you just have greater than as a or equal to, then you have the weakly dominant uh, concept, also weakly dominant strategy. So let's look at an example for the game in the table down here. 1 3 is a weakly dominant strategy for player 1. So what that means is the payoff for player 1 compared to the other two strategies is always greater than or equal to. So we have 1 is greater than 0, is greater than 0, so that checks out. 4 is greater than 0, greater than 1. And 4 is greater than 1, greater than or equal to 4 actually. And so S11 is a weakly dominant strategy for player 1. Okay, so you may want to just play around with that and see if there are any other weakly dominant strategies for or strictly dominant strategies for player 2, just to convince yourself of the concept here. Okay, so it's just again, it's just taking the concept of strict dominance and weak dominance, which was pairwise when we first defined it, and then we're defining it more globally here. And this is more at the heart of how you go about finding solutions to these problems. The issue is that you may not always have a strictly dominant or weakly dominant strategy. And then you get into these probabilistic models where you play different strategies a certain percentage at the time. But we'll get into that later. On this slide, I have an example of a game with 3 players. It's an extension of the prisoner's game, but now we have 3 players. And so I have it listed here, players 1, 2, and 3. And they each have 2 pure strategies, either cooperate or defect. So the strategy profiles, this cross product we talked about before, there would be a total number of 8 possible combinations. And I'll go through the example down here at the bottom. In fact, let's look at that first. So the first complication you see here is that you can't represent this with a matrix. You sort of have 3 dimensions now. So one way to do it is using a cube, but that's rather hard to put in the paper. So we've done it by breaking the cube into 2 parts. You notice here we have one of the possible plays for player 3, and then we show the combinations for players 1 and 2 in the context of player 3 making the play 1, which is basically cooperate. And then we have a second matrix where player 3 takes option 2, in other words, it defects, and then we show all the options for players 1 and 2 relative to player 3. So between these 2 matrices, we have all the profiles shown here. And then the payoffs are listed here. Now you need a 3-tuple, so just take this one here. So if player 3 defects, or excuse me, cooperates, because it's a 1. So player 3 cooperates, player 1 cooperates, and player 2 cooperates, then they each have a payoff of 4 based on this model here. So we have strict dominance. We can look at that. It's a little bit more involved now. So S12 strictly dominates S11. And you have to look at both matrices now to see that. So when player 3 has these 2 different options, you have to look at in both cases. So you notice here, again, we're focused on player 1 in this case. So we have to look at the first entry. So 5 is bigger than 4, 3 is greater than 2, 3 is greater than 2, and 1 is greater than 0. So that's true. In the case of player 1, strategy S12 strictly dominates S11. So player 1 would go for the strategy S12. So that's strict dominance. Then dominant strategies in general, this is completely symmetric. So if you look at, say, S22 for player 2, we look at the comparisons here. 5 is greater than 4, 3 is greater than 2, 3 is greater than 2, and 1 is greater than 0. So S22 is strictly dominant or dominant over S21. And so player 2 would play S22, picking the dominant strategy. In all cases, it would always make that selection. And we can do the same thing for S32, that's actually dominant over S31. And we need to compare each one of these to the same cell on the opposite side here. So, and looking at the third entry, so 3 is greater than 2, 5 is greater than 4, 1 is greater than 0, and 3 is greater than 2. So in each case, the dominant strategy is the second one to defect. And so you would have all 3 players defecting, and that would bring you to this solution here. And it has the same paradox or dilemma as the 2-player prisoner game, because you have the possibility of 4-4-4, which is a better solution for all three players. But if each one plays their best strategy, their strictly dominant strategy, then they're all going to play the effect, and you're gonna have a 1-1-1 here. And that's what I explained on the last line here. Let's see, and I had one other example here in terms of a best response. So, for example, players 3 best response to S11, S21. Let's see, where is that? That's this here. So, or this here. So what would be the best response? Well, you could either get a 4 or a 5. So it would go for this response here. So it would be S 3, 2 in that case. Okay, so that's a 3-by-3 example. It gets even harder if you have 4 players. These matrix representations become rather difficult because you had a 4th dimension and you need to start replicating things. Okay, so this is the last slide in this lesson, but I have several more lessons. So if you like this, please give it a thumbs up and stay tuned for a few more lessons on this topic.